Any great software program begins with a plan and a well-defined procedure. Fortunately, there are various software development processes from which to select before beginning the next project. But how do you know which software development process is best for you? In this video, the learning outcomes that are expected are the following. First is to explain the overall process of developing new softwares. Second is to explain the differences between software development methodologies. Third is to understand the different types of programming languages used to develop softwares. Fourth is to understand some of the issues surrounding the development of websites and applications. And lastly, to be able to identify the 4 primary implementation policies. As a manager, one must consider every requirement from stakeholder connectivity, growth, and to the specifications in the ongoing maintenance. These steps are all pretty much the same across any software development process organizations use. However, the order and sequence can change depending on the organization's needs, goals, and team size. For example, some steps might be combined, duplicated, or run in parallel. Whether you intend it or not, any piece of software follows a common path from conception to deployment. The phases of this path are collectively termed as the Software Development Life Cycle, or SDLC for short. The SDLC is a series of phases that occur during the creation of software. The value of providing a consistent process and understanding your implementation steps cannot be underestimated. Without a software development strategy in motion, one must expect slower timelines, lower consistency, or even failure. Worse, the developers would be at a loss about what to make. Aside from that, the project managers may have no idea how much progress has been made or whether you are on schedule or on target to finish the project. The first on the list is preliminary planning. This step usually means looking into alignment. How does this project connect to your company's larger mission and goals? Resource availability and allocation. Do you have the people and tools you need to take this on? Third is project scheduling. How does this project fit within your company's goals and other tasks? Lastly, cost estimation. How much is it going to cost? The planning phase ensures that you get off to a good start. As managers, including all divisions that will be affected by this initiative, such as project managers, engineers, logistics, defense, and key stakeholders, would be rational. At the end of the planning phase, you should have enough information to put together a high-level scope of work which details the plan of what's being built, why it's being built, and how it's all coming together. Thus, the reason why the second step is system analysis. The following step is to comprehend the project's technological specification. Any piece of software, whether an app, a website update, or a new feature, must solve a customer problem. As you move on from the planning phase and continue to fill out the other requirements of a specific system, some key questions are: what problems does this solve? Who's going to use it and why? What sort of data, input or output is needed? Will you need to integrate it with other tools or APIs? How will you handle privacy, or security? When the development team has the answers to these questions, they will begin to figure out technological specifications, testing terms, and choose a technology stack. This is also the stage at which you can begin preparation or break down large tasks into more actionable steps. The third phase in the SDLC process is system design. With the specifications in mind, it is time to begin developing how this program will look and work. We're not concerned about aesthetics here, but rather about functionality and flow. As Steve Jobs famously stated, design is not just what it looks and feels like. Design is how it works. Depending on the software development process your team is using, this step of the SDLC can include creating basic wireframes to demonstrate how interactions can function in the software, or creating more full-fledged prototypes to test on users using a platform like Marvel or InVision. You may also choose to require beta users to fill up a user feedback form to get an idea or innovate the program more so it better fits the users. However you choose to design it, this step helps your team and your client, whether a customer or a stakeholder, validate ideas and get valuable feedback before you commit your ideas into programming or code. With everyone on board with the software's proposed functionality and design, it's time to build according to the requirements. Thus, the fourth step is programming. This is, without a doubt, the most difficult and potentially dangerous stage of the SDLC. It is in this step that the code finally gets written in the programming phase. Using the system design document as a guide, programmers develop the software. The result of this phase is an initial working program that meets the requirements specified in the system analysis phase and the design developed in the system design phase. These tasks are done by persons with titles such as developer, software engineers, programmers, or coders. Nevertheless, the aim in this step is to stick to the requirements as specified from the previous step and create an effective software. The fifth phase in the SDLC is testing. When your team is designing the software, you will most likely be reviewing, tracking, and repairing bugs at the same time. However, if the features are complete and the software is considered ready to go, you will need to do further in-depth testing. This could imply introducing the app to a selected number of beta users or using another software to monitor how users interact with it. Though testing can be another lengthy stage of the SDLC, it is critical so as to avoid delivering buggy applications to actual customers. Bugs have the potential to ruin your credibility, cost you money, and most of all, consume hours of development time that should have been spent on developing new features. The fifth phase in the SDLC is testing. When your team is designing the software, you will most likely be reviewing, tracking, and repairing bugs at the same time. However, if the features are complete and the software is considered ready to go, you will need to do further in-depth testing. This could imply introducing the app to a selected number of beta users or using another software to monitor how users interact with it. Though testing can be another lengthy stage of the SDLC, it is critical so as to avoid delivering buggy applications to actual customers. Bugs have the potential to ruin your credibility, cost you money, and most of all, consume hours of development time that should have been spent on developing new features. The next phase in the SDLC process is implementation. With the coding and testing, it's time to launch the software to all target users. What we're talking about here is pushing your code into production, not coming up with and implementing a go-to-market strategy, because that's more up to your sales and marketing teams. In most companies, this step is automated using a continuous deployment model or application release automation tool. The last phase is maintenance. The SDLC does not end once your app is released in the market. The process is called life cycle for a reason. The completion of one process is just the beginning of another, and the same is true for its post-launch. Requirements and consumer expectations are constantly changing, and as users continue to use the program, they will undoubtedly discover glitches, require new features, and request additional or different functionalities. Many of these requests can be routed back into the priority list so that they can be prioritized and added to your software roadmap.
Rapid application development, or the RAD methodology, focuses on immediately creating a working model of software, gathering user feedback, and using the feedback on updating the working model. A final version then is developed and introduced after several iterations of development. There are 4 phases of the RAD methodology, namely requirements planning, user design, construction, and cutover.
The first phase of the RAD methodology is requirements planning. In comparison to SDLC, this phase plays the preliminary analysis, system analysis, and design phases all in one. This method, when building a system, we first identify the problem pertaining to the preliminary analysis of the SDLC, and then we think of how we solve this and think of a draft of procedures, but we don't actually do it yet. This is actually the system analysis already, and then the details comes after, which is part of the design phase. The second phase of the RAD methodology is user design, where representatives of users collaborate with the system analysts, designers, and programmers for an interactive development of the system. Now let's proceed with the third phase, which is construction. In this phase, the developer examines the system and mainly determines what needs to be adjusted, and it goes back again to the user design, where the change is added until the desired version is achieved. This is why this phase is placed parallel to the former in the diagram. Finally, the cutover phase, which is the last step, includes shifting from the old to the new software, and this involves 3 approaches. First is to entirely abandon the old system and proceed with the new one. Second is to make use of some of the functions of the old system along with the new ones, while the third is running both the systems and then recording the observations regularly to confirm accuracy. Aside from RAD, we also have agile methodologies, and from what you can see in the screen, it is how this process is being illustrated. This makes use of the incremental changes, focusing on quality and details. Similar to the previous one, this phase also involves iterative development user interaction, and flexibility to change. The diagram you can see emphasizes iterations in the center of the agile development. You should notice how the building blocks of the developing system move from left to right, a block at a time, and not the entire project. Blocks that are acceptable are returned through feedback, and the developers may make the necessary modifications. Finally, notice the daily review at the top of the diagram. Agile development means constant evaluation by both developers and the customers. Here are the characteristics of the Agile methodology. It still is composed of a team that consists of developers and users. It also involves a constant monitoring and control system. It also has short time increments and fosters progress to the stakeholders upon each iteration process. Ultimately, this process aims to provide flexibility of an iterative approach without risking the quality of its output. Another process is the lean methodology. This focuses on taking an initial idea and developing a minimum viable product or MVP. This MVP is a working software application with just enough functionality to demonstrate the idea behind the project. The build, measure, and learn cycle is a feedback loop that is said to be the core component of the lean startup methodology. It aims to turn uncertainties, assumptions, and risks into knowledge and certain things that will eventually guide organizations and business towards progress. Through this process, the key unknowns can actually be transformed into knowledge that a startup can use in its product development and business operations as a whole. Now let us look at the phases of this process. The first phase is to build, which aims to develop its MVP, which means minimum viable product or the bare minimum product that can be built to test a number of assumptions or hypotheses formulated as quickly as possible. Like any other processes, this phase includes determining the problem, designing, building, and running the experiment. The next phase is to measure. It determines whether progress is being made or not, and this involves measuring the results obtained from the experiment performed during the build phase. It involves data analysis, organization. Learning is the last phase of this process. This is centered to the question, should it persevere or should it pivot? Persevere in this context means carrying on with the same goals, while pivot means changing or shifting some or all of the aspects of the product strategy. Afterward, you will have to document your findings and share them.
Developers create programs using one of several programming languages. A programming language is an artificial language that provides a way for a developer to create programming code to communicate logic in a format that can be executed by the computer hardware. Over the past few decades, many different types of programming languages have evolved to meet a variety of needs. One way to characterize programming languages is by their generation. Early languages were specific to the type of hardware that had to be programmed. Each type of computer hardware had a different low-level programming language. In those early languages, very specific instructions had to be entered line by line, a very tedious process. The first generation is called the machine code. Programming was done in the machine language format, done by directly setting actual ones and zeros, or called the bits, in the program using binary code. Assembly language is the second generation language and uses English-like phrases rather than machine code instructions, making it easier to program. An assembly language program must be run through an assembler, which converts it into machine code. Third generation languages are not specific to any type of hardware on which they run and are similar to spoken languages. Most third generation languages must be compiled. The developer writes the program in a form known as source code. Then the compiler converts the source code into machine code, producing an executable file. Fourth generation languages are a class of programming tools that enable fast application development using intuitive interfaces and environments. A fourth generation language has a very specific purpose, such as database interaction or report writing. These tools can be used by those with very little formal training in programming and allow for the quick development of applications. We continue to use lower level languages even though they require additional effort because we want to maintain control and efficiency. Lower level languages are much more efficient and execute much more quickly. Secondly, the developer has finer control over the hardware. Sometimes a combination of higher and lower level languages is mixed together to get the best result. This is because higher level languages create better overall structure and interfaces, while lower level languages provide more precision and speed. Aside from identifying a programming language based on its generation, we can also classify it through the distinction of whether it is compiled or interpreted. A computer language is written in a human-readable form. In a compiled language, the program code is translated into a machine-readable form called an executable that can be run on the hardware. Interpreted languages require a runtime program to be installed in order to execute. Each time the user wants to run the software, the runtime program must interpret the program code line by line, then run it. Interpreted languages are generally easier to work with, but are also slower and require more system resources. A procedural programming language is designed to allow a programmer to define a specific starting point for their program and then execute sequentially. All early programming languages worked this way. As user interfaces became more interactive and graphical, it made sense for programming languages to evolve, to allow the user to have greater control over the flow of the program. An object-oriented programming language is designed so that the programmer defines objects that can take certain actions based on input from the user. In other words, a procedural program focuses on the sequence of activities to be performed, while an object-oriented program focuses on the different items being manipulated. To write a program, you need little more than a text editor and a good idea. However, to be productive, you must be able to check the syntax of the code and in some cases compile the code. To be more efficient at programming, tools such as an integrated development environment (IDE) or computer-aided software engineering (CASE) tools can be used. For most programming languages, an integrated development environment (IDE) can be used to develop the program. An IDE provides a variety of tools for the programmer and usually includes an editor, which is used for writing the program. Commands are automatically color-coded by the IDE to identify command types. For example, a programming comment may appear in green and the programming statement might appear in black. Next, a help system. A help system gives detailed documentation regarding the programming language. Third, the compiler/interpreter. This converts the programmer's source code into machine language so that it can be executed on the computer. Fourth, a debugging tool. This assists the developer in locating errors and finding solutions. And lastly, a check-in and check-out mechanism. This tool allows teams of programmers to work simultaneously on a program without overwriting another programmer's code. While an IDE provides several tools to assist the programmer in writing the program, the code must still be written. Meanwhile, computer-aided software engineering or CASE tools allow a designer to develop software with little or no programming. Instead, the CASE tool writes the code for the designer. CASE tools come in many varieties, but their goal is to generate quality code based on input created by the designer.
Next, we're going to discuss about issues surrounding the development of websites and mobile applications. First, we discuss common sidebars when it comes to developing websites. So in the early days of the World Wide Web, the creation of a website required knowing how to use hypertext markup language or HTML. There are many different ways of creating a website, but the final product that transmitted to a browser is still HTML. So HTML is the text language that enables developers to define the different components of a web page. These definitions have handled through the use of HTML tags with the text between the tags or brackets. Just like in our lab activities, we were taught about how to show a word in italics, to link to another web page, or insert an image to be displayed on a web page. Next, developers should know how to use cascading style sheets or CSS. While HTML is used to define the components of a web page, cascading style sheets are used to define the styles of the components on a page. The use of CSS or cascading style sheets allows the style of the website to be set and stayed consistent throughout. And lastly, when developers create a website, they do not write it manually in a text editor. So developers commonly use a web design tool that generates HTML and CSS for them. One example tool is the Adobe Weaver. This tool allows the designers to create a web page that has images and interactive elements without writing a single line of code. However, professional web designers still need to learn HTML and CSS in order to have full control over the web pages that they're developing. The next that we're going to discuss is about the sidebars when it comes to developing mobile applications. So generally speaking, building mobile application has the same way in building an application on a computer. Developers should know and understand the requirements for the application, designing the interface, and working with the users. So these are the steps that need to be carried out when we develop mobile applications. There are 5 primary differences about building an application for a mobile device. So first, breakthroughs in component technologies. So mobile devices require multiple components that are not only smaller, but more energy efficient than those in full-size computers such as laptops or desktops. For example, low-power CPUs combined with longer life batteries, touchscreens, and Wi-Fi enable very efficient computing on a phone, which needs to do much less actual processing than their full-size counterparts. Second, sensors have unlocked the notion of context. So the combination of sensors like GPS, gyroscopes, and cameras enables the device to be aware of things like time, location, velocity, direction, altitude, attitude, and temperature. Location, in particular, provides a host of benefits. Third, simple, purpose-built, task-oriented apps are easy to use. So mobile apps are much narrower in scope than enterprise software and therefore easier to use. Likewise, they need to be intuitive and not require any training. Fourth, immediate access to data extends the value proposition. So, in addition to the app providing a simpler interface on the front end, cloud-based data services provide access to data in near real time from virtually anywhere like banking, travel, driving directions, investing. So having access to the cloud is needed to keep mobile device size and power use down. Last, app stores have simplified acquisitions. So developing, acquiring, and managing apps have been revolutionized by app stores such as Apple's App Store and Google Play. Standardized development processes and app requirements allow developers outside Apple and Google to create new apps with a built-in distribution channel. So, average low app prices, including many of which are free, have fueled demand. So when we talk about mobile app differences, building a mobile app for both iOS and Android operating systems is known as cross-platform development. So there are a number of third-party toolkits available for creating your app. And many will convert existing code such as HTML5, JavaScript, and etc. However, if your app requires sophisticated programming, a cross-platform developer kit may not meet your needs. Another mobile app differences is the use of responsive web design or RWD. So this focuses on making web pages render well on every device, such as desktop, laptop, tablet, or smartphones. Through the concept of fluid layout, responsive web design or RWD automatically adjusts the content to the device on which it is being viewed.
In terms of implementing a new system, there are 4 primary implementation policies. They are direct cutover, pilot implementation, parallel operation, and phased implementation. The first implementation method I will be sharing is the direct cutover method. In the direct cutover method, the organization sets a specific date wherein users in the organization will stop using the old system and will shift to the new system. The advantages for the direct cutover method are that the switch from the old system to the new system is fast and it is the least expensive because support is provided only for the new system. However, this implementation method also carries the most risk, since if the new system has any operational problems or if users are not properly prepared to adapt the new system, it could be bad for the organization. The second implementation method I'll be discussing is the pilot implementation method. The pilot implementation method is where a subset of the organization is chosen to use the new system before the rest of the organization. This group is called the pilot group. Compared to the direct cutover method, if there are problems in implementing the new system in this pilot group, then the impact to the organization will be smaller, and the expense needed to support the use in this smaller group is also smaller. However, this implementation method is also slower than the direct cutover method because of the wait until the new system is successful in the pilot group. The next method is the parallel operation method. The parallel operation method allows both the old and the new system to work simultaneously, so users can use both. The advantage of this method is that in the case wherein there are problems in the new system, users can just switch to using the old system. In this way, the new system is being tested while the old system is there as a safety net. The disadvantage of this implementation method is that it is the most expensive method out of the 4 because the organization is essentially running 2 systems, so work will be duplicated on both and support is needed for both. so it is more expensive. The last implementation method I will be sharing with you is the phased implementation method. In a phased implementation method, different functions of the new system will be gradually implemented with the corresponding function in the old system being turned off. The advantage of this method is that each function of the new system can be tested before the whole system is implemented. The disadvantage is that it is slower due to needing to make each function successful before implementing the next. The choice of implementation method to use is dependent on the complexity of the old and new systems, and also the risk the organization is willing to take. With the implementation of a new system, changes are sure to occur in an organization. Change should never be introduced in a vacuum. The organization should communicate with those affected by the change beforehand and try to minimize the impact of the changes. After implementation, the new system enters the maintenance phase. While the system is being used, bugs might be found, so changes need to be made or new features might be requested. The IT management must ensure the system is aligned with business priorities and continues to run well.